Okay, so first I'm going to be going over activity number 14. This one includes just chapter 11. So this is going to be number 1, and what we have is a block that is connected to a spring, and what we're told is that it's oscillating between 10 centimeters and 80 centimeters. What we're also given is that it is oscillating 10 times per 30 seconds. So for a period, what a period is how long does it take for it to oscillate once? So how many seconds per oscillation? So we do 30 seconds over 10 oscillations, which gives us 3 seconds, which you should, do sig figs because he cares about that. And then we're looking at frequency, which is how many oscillations per second. So now we do 10 oscillations over 30 seconds, which just gives us 0.33 oscillations per second. So, and then for amplitude, what amplitude is the max displacement that the block travels from its equilibrium state. And when a block is, when it's oscillating like this, its equilibrium state is always right in the middle. So the distance we're looking for is right here between its equilibrium state and how far it oscillates. So what we do is look at the difference between these two distances, which is 70 centimeters, and divide it by 2. So that's going to be 35 centimeters or 0.35 meters. So now we're going to look for the max speed of the mass. And what I wrote out here is the energy conservation theorem. And I don't think this is something you have to memorize. I'm pretty sure he'll put this on the back of the test. One thing that you will have to remember though is that for a mass that's oscillating on a frictionless table, its max speed is always going to be where x equals 0. So we're going to put that to 0. And the reason why is because if you think about it, like if you have a spring and like let's say this is the block and this is its equilibrium state. If you pull it back and you let go, it's going to speed up and up and up and up, and then when it passes by 0, it's going to be its max speed, because once it passes it, it's going to be starting pulled back the other direction. So right here at x equals 0 is where its max speed is. So what we're looking for is the velocity here. And after some algebra, you get v max equals its amplitude times square root of k over m. The only thing we have from this equation is its amplitude. We don't have the spring constant, and we don't have the mass of the block. So what you need to do is find something you can substitute into there. So another thing that we know is that t equals 2 pi square root k over m. And when you rearrange this, you get square root k over m. Oh, I'm sorry, this is m over k. So when you rearrange it, you get square root k over m equals 2 pi divided by t. So you see this matches up right there. So we replace square root k over m with 2 pi over t. So this goes to amplitude times 2 pi divided by t. So then when you just plug in the amplitude, 0.35 meters is there, and 3 seconds into t, you are given 0.733 meters per second. And I want to worry so much about like this whole rearranging to plug in. I don't know if he'll put a question like that on the exam, but just the strategy is if you're stuck with something that has a value you don't know, just look at the other equations for amplitude, frequency, or period and see if you can rearrange and plug it in. And for number 2, what we're told is that we have a 3.5 kilogram block attached to a spring with a spring constant of 16 newtons over meters, and it lies at rest on a frictionless surface. A student then hits it with a hammer and almost instantly gives it a speed of 40 centimeters per second, which I converted to 0.40 meters per second. And we're told to treat this as a conservation of energy problem with an initial speed of 40 centimeters per second. So what part A wants is the amplitude. So what we're looking for is amplitude. And what amplitude is when it's how far it travels before it starts coming back. So we're told to treat it as energy conservation problem. And the formula for that is this: the kinetic energy plus the potential energy equals kinetic final energy plus potential final energy. So one thing you need to know is that when it's sitting at rest and it has a velocity, because technically it hasn't moved yet, but we did give it some velocity from the hammer hit, it has kinetic energy, but it has no potential energy at the start. Once it stretches all the way out and comes to right here, its velocity is technically 0 because it's reached all the way and it's about to come back. So we know it has no kinetic energy. So now what we're left with are these two, which look like this. 1/2 mass times velocity squared equals 1/2 spring constant times x squared. And what we're trying to find is this x, because that's going to give us our amplitude. So we have some of this stuff. We do 1/2 mass 3.5. Velocity we have, which is 0.40 meters per second squared equals 1. All right, so it looks good. All we're left with is with our x now, and you just plug this into your calculator and solve for it. And we get x equals plus or minus 0.187 meters. So amplitude is never negative. It's just how far it travels from its equilibrium state. So amplitude equals 0.187 meters. Okay, now we're gonna do part B. But we're gonna say the amplitude. Part B. It's asking for what is the block speed where x equals 1/2 of the amplitude. So instead of looking for what the block speed is, so looking at what's all the way at the end, we're looking at the middle right here, because this is half the amplitude. This is full amplitude, this is half of it. So what we want is to find this speed right here. So again, we look at this equation again, the energy conservation one. And again, at the start, it has no potential energy because it's technically still sitting still. And then at the final right here, it is moving still and it's still stretching out. So it still has kinetic energy and it still has potential energy. So let's set this up, 3.5. What is it? And this is what we're looking for, is this velocity final squared right there. And then I'm gonna try and squeeze this in here. We have 1/2 16. And then the x right here is again half the amplitude. We have the amplitude from the last part A. So then we do 0.187 over 2 and square it. Okay, that didn't fit that good. But now as you see, we're just left with this one variable, which is velocity final squared. So again, just plug all this into your calculator. And what you're left with is velocity final equals 0.346 meters per second. So let's see if you say that. The things to take away from this example is when a spring is stretched out fully, all it has left is potential energy because the string is stretched out and it's about to come back. It has all that potential energy stored into the spring that's going to shoot it back. And when it's sitting still, it just has kinetic energy, no potential energy because it's not moving yet. And that's number 2. All right, so now we're going to work on number 3. So what we're told is we have a 215-gram ball is tied to a string hanging from a ceiling. And I converted that to kilograms. You just move the decimal 3 steps to the left to turn it from grams to kilograms. It is pulled an angle of 3.50 degrees and released to a swing as a pendulum. A student with a stopwatch finds that 10 oscillations takes 14.9 seconds. So one thing is that the degrees we don't need to use the degrees for anything. It's just like a scare factor, I guess. Part A is just asking for the period, which is how long does it take for one oscillation. So how many seconds per oscillation? So 14.9 divided by 10 is 1.49 seconds. And then frequency. So this is T, right? Period is represented as T. Frequency equals 1 over T. It's just the flip of it. And when you plug that into a calculator, which you do 1 over 1.49 seconds equals 0.671 oscillations per second. So then that's the answer for that one, for frequency. And then for C, what it asks for is what is the length of the string? And this is an equation I believe that we're going to be given on the back of the exam, so I'm not sure yet if you have to like memorize it, but we usually get these equations given to us. So we know what the period T equals, 1.4, because we're looking for L. So 1.49 seconds equals 2 pi square root L divided by G, and that's gravity, which is 9.8 meters per second squared. This again is just going to be, you know, doing algebra on your calculator, you know, divide by 2 pi, square it, and then multiply by 9.8 meters per second. And what you're left with is L equals 0.551 meters. All right, and then the last one asks, on the moon, gravity is 1.62 meters per second. So write that out. And then what would the period of the same pendulum be on the moon? So again, we're going to look at this equation, but what we're looking for now is the period, which is T. So that's what we're looking for. What we are given is the gravity of the moon, and we also have L from the last problem, which is the length of the string. So we just do period equals 2 pi square root the length of the string, 0.551 meters, over the gravity of the moon. And when you just run this through your calculator, and you get 3.66 seconds. All right, so now we're going to do number 4. What we're told is we have a 1.2 kilogram block attached to a horizontal spring with a spring constant of 280 newtons over meters. The block is at rest. A 18-gram bullet, which I converted to 0.01 kilograms, just move the decimal 3 to the left, is fired into the block and it sticks, so it lodges itself into the block. The subsequent oscillations have an amplitude of 6.3 centimeters, which I turned into 0.063 meters. For part A, what was the speed of the combined block plus the bullet immediately after the collision? So the way I figured this one out was I just used energy conservation, and this is going to be another thing that another equation that we should be given on the back of our exams and the keys. So it's 1/2 times the spring constant times the amplitude squared equals kinetic energy plus elastic energy. That's math. All right, so let's see, what was the speed of the combined block plus a bullet immediately after the collision? So what we're looking for is the velocity of the block and the bullet right after the collision. So immediately after the collision, it hasn't moved yet. So that means x is 0. So that goes to 0. So all we're left with are these. We have the spring constant, we have the amplitude, and we have the mass is going to be the mass of the bullet plus the mass of the block because it lodges itself into it. So we have all right, so this is the mass of the block plus the mass of the bullet. And so if you look at it, all we're left now is the final velocity. And that's all that we need to solve for. And when you solve for that, just plug into your calculator, you get 0.96 meters per second. All right, and then for part B, it's asking what was the speed of the bullet just before it hits the block. So this is gonna be another energy conservation problem. Oh no, this is. All right, and then for part B, it's asking for the speed of the bullet just before it hit the block. And if you think about it, we have the mass of both of the objects, the bullet and that, and we know the velocity, the final velocity after it lodges itself into it. So a really easy way to do that, to figure this one out, would be to use the conservation of momentum theorem. m1v1 plus m2v2. That's initial. Equals m1v1 plus 2. So when we look at this, if you remember beforehand, it was only the bullet that was moving. The velocity of the block, it was sitting still, so that goes to 0. And then for the final part, if you remember, the bullet lodges itself into it, and they have the same velocity. So it becomes m1 plus m2 times velocity final. So when we set this up, we're looking for this v2. This is the initial velocity of the bullet. So we have 0.018 kilograms times v initial equals 0 kilograms plus 0. Velocity final from the last equation, 0.96. All right, so now we're just left with velocity initial, and when you solve for that, it's going to be 64.96 per second. And that's it for activity 14.